Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. We would also greatly appreciate if you consider supporting us on Patreon. Please check the link in the description for more details. My name is Seva, and today we're finally completing our discussion of the efficient portfolio frontier and modern portfolio theory, and we are investigating the general case how to build the efficient portfolio frontier, this pretty curve that relates expected return and risk, the standard deviation of a portfolio, when you have got more than two stocks and without even using MS solver. So to do that, one has to use quite complicated, on the first glance at least, matrix algebra. And the derivation of the formulas we're going to discuss today has been completed in the early 1970s by famous economist Robert Merton. So to start with, we have got our usual template, our 5 stocks that we have already constructed a portfolio with in the previous video using Excel Solver. These stocks, just to recap, are Tesla, Apple, Microsoft, Walmart, and Caterpillar. And we have got S&P 500 return so that we can use CAPM, Capital Asset Pricing Model, to derive expected returns that are more realistic than the historical average annualized returns. So here we calculate daily returns for the S&P 500 throughout the whole sample period, and our sample period is a 10-year window from mid-September 2010 to mid-September 2020, so quite a representative sample period. And in a similar fashion, daily returns for all 5 of our portfolio stocks, our investable universe stocks, the stocks that we might consider investing and allocating a proportion of our capital towards in an efficient portfolio. And then we calculate historical returns of every single stock using product 1 plus and raising to the power 1/10 because we have a 10-year period. We also calculate the historical return and we use it as the expected return for the market. We calculate our betas, that are just the slopes of a linear regression of stock returns onto daily market returns, and then we use the logic of CAPM, so risk-free rate plus beta times market return minus risk-free rate, to calculate the CAPM expected returns for the 5 candidate stocks, the stocks from our investable universe. To recap all of that in greater detail, please consider watching the previous video in our series when we were investigating various assumptions that one can use to derive expected returns. But today we're more concerned with actually the covariance matrix. The covariance matrix just inputs the annualized covariance of every single stock with every other stock, and therefore on this diagonal we have got variances, because by definition the covariance of a random variable with itself is just this random variable's variance, and we have got also pairwise covariances of every single stock of among these 5 with every other single stock. And we need this covariance matrix. The covariance matrix is the centerpiece of the Merton's matrix optimization framework. The first step, and it's a very crucial step to derive every single other result in Merton's model, is to calculate the inverse of the covariance matrix. To do that, we have got a 5x5 template over here, so we can just select that and type in inverse, which stands for matrix inverse, calculate the inverse matrix of the covariance matrix, so of this 5x5 matrix. We close the parentheses, enforce this formula using Shift-Control-Enter, and it gives us the inverse of the covariance matrix. Make sure that it's symmetric. If it's not symmetric, it means there is some mistake in your covariance calculations. In our case, it's indeed symmetric, so we can feel good about it. And later on, we will use this covariance matrix to calculate a bunch of vectors that will then characterize our investable universe in terms of the efficient portfolio frontier. But first of all, we need 2 starting vectors that would also guide us in all our following analysis. The E vector is just a vector of ones of length that is equal to the volume of your investable universe, to the size of your investable universe. As we have got 5 stocks, our E vector is a vector of 5 ones. So 1, 1, 1, 1, 1, because we've got 5 stocks again. And our R vector, and it's pretty clear from the name, is the vector of expected returns. So we can just refer to the expected returns we got from CAPM over here and enforce this formula using Shift Control Enter. And now we can start the good stuff. The portfolio analysis in the matrix model of Merton starts with calculating the H vector and the G vector. And those vectors are just the products of E and R vector, respectively, onto the inverse covariance matrix C to the power of -1. That's a standard notation of inverse matrices. C is the covariance matrix, C for covariance, and C-1 is the inverse covariance matrix. So here we can just apply the matrix multiplication formula and multiplying the row vector E, the row vector of ones, onto the inverse covariance matrix over here. And we can close the parentheses and enforce this formula using Shift Control Enter, and this will return the H vector that is crucial for risk minimization. How? We'll talk about it a little bit later. For the G vector, we need to do exactly the same, but instead of the E vector, instead of the vector of ones, we need to input the vector of expected returns, as per CAPM in our case, and also multiplied by the inverse covariance matrix, C to the power of -1. Close the parentheses and enforce these formulas in Shift Control Enter again. And that will give us our G vector. What is useful regarding H and G vectors is that they can be used to calculate 4 portfolio constants, alpha, beta, gamma, and delta. And don't be confused, this bit has nothing to do with the betas we calculated over here. It's just an unfortunate coincidence that can sometimes leave you a little bit puzzled. But bear with me. Those 4 portfolio constants characterize our investable universe, and they define uniquely the efficient portfolio frontier that exists in this investable universe for stocks with such a covariance matrix. This is our input that then generates the efficient portfolio frontier as an output, and the expected returns as an input again. So if you've got a number of stocks characterized by these returns, expected returns calculated using some model, CAPM in that case, and pairwise covariances, then you can be sure that your efficient portfolio frontier can be characterized by those 4 parameters. And these constants can be calculated, again, using scalar products of vectors E or R and vectors, transposed vectors H and G. Again, here, H and G, T is a standard notation for transposed vectors, and we'll do exactly that. So for alpha, we will need to multiply the row vector of E by the column vector of H. And here, as H vector is a row vector in that case, we'll just need to transpose H, and everything will be fair and square. So again, we just apply the matrix multiplication formula and input E vector as it is, it's a row vector, and because it's a scalar multiplication, we need a column vector as our second argument. And because, again, H is a row vector, we need to transpose it first. So transpose, literally a function in Excel ready to go. Input our H vector there, close the brackets again, and enforce the matrix multiplication formula using Shift Control Enter. And we see that our constant alpha is 34.02 approximately. For the constant beta, we need to do exactly the same, but input G vector instead of H vector. So being lazy, we can just copy this formula, paste it over here, and refer to G instead of H. And again, Shift Control Enter does the job. And for the constant gamma, we need to multiply the G vector on the left, not by the row vector of ones, but by the row vector of expected returns. So here again, we can be lazy once more, paste the formula into this cell, and instead of the E vector, drag it down to the R vector. And pressing Shift Control Enter, we're getting our gamma constant. And now the final constant that we need to compute is the delta constant, and delta is just alpha times gamma minus beta squared. And it gives us 2.78. Now we can actually, straight away, without even calculating the efficient portfolio frontier function, we can already know what is the minimum variance portfolio for such an investable universe. To do that, we can just divide the H vector by the constant alpha. And that will give us a vector, because we divide a vector by a constant, it will give us a vector of length 5 that will be the allocation of weights towards our 5 initial stocks that would give us the minimum variance for such an investable universe. Let's try it. Let's consider dividing the H vector by the alpha constant, and we get the portfolio weights that sum to 100%. So again, there is something going on here. It can be interpreted as portfolio weights, but is it actually a portfolio that generates minimum variance? Let's check that here. So here we have got our expected return already calculated using sum product, so multiplying the weighted average for those stocks. But actually, you can do even easier than that. You can actually use the constants that you obtain over here to get the return and risk of the MVP. MVP standing for minimum variance portfolio, not most valuable player. So the return of the MVP is equal to beta divided by alpha. So divide beta by alpha and getting 8.94%. And that's exactly what you get if you weigh the expected returns you input into the model by the weights you obtain from dividing the H vector by the alpha constant. So again, some reinforcement of this result being correct here. But what about the risk? Well, the risk, the sigma squared, the variance of such a minimum variance portfolio, is just 1 over alpha. So as its variance, to calculate the standard deviation, you just need to take the square root of 1 over alpha. And we can see here that the risk of the minimum variance portfolio is 17.14%. And we can compare it to the risk of individual stocks and see that indeed the diversification benefits of allocating your capital towards a number of stocks instead of one single stock allows you potentially to achieve a level of risk that's even lower than the lowest risk of individual stocks, which is again why diversification is a good thing. But if you are not entirely persuaded by this analysis being correct, you can actually just calculate the variance straight away, directly, using weights and the covariance matrix. To do that, you can just apply the matrix multiplication function, have a row vector of weights first, and then multiply it by the result of the matrix multiplication of the covariance matrix, and not the inverse covariance matrix, but the initial covariance matrix over here, that is multiplied on the right by the transposed, so column vector, of the weights we have got here. And if you close the parentheses correctly, enforce this formula using Shift-Control-Enter, you will get the variance of this portfolio. But we need the standard deviation, the volatility, so we'll just type in the square root over here. And if we enforce this formula, we get exactly 17.14%. So it means that this formula for the MVP, for the minimum variance portfolio, indeed gives us, as an output, correct portfolio weights that can be easily interpretable as capital allocations towards particular stocks. And we can see here that the minimum variance portfolio heavily invests in Walmart. It's unsurprising, Walmart being the least risky individual stock here. And it does invest quite conservatively into Tesla. Around 1% of your capital goes into Tesla if you are a very risk-averse investor that only cares about minimizing risk. And that's again unsurprising given the fact how risky Tesla is as an individual stock. So the results of the model are actually quite intuitive and understandable. But what about the efficient portfolio frontier? What about generating the curve? Well, the curve is being uniquely defined by these 4 portfolio constants. So they allow you to get a functional relationship between expected return of a portfolio and its risk, its standard deviation. So we need to consider various values of expected return that we might want to get, and the formula that relates expected return to risk using these constants will get you the level of risk for an efficient portfolio with such level of expected return again. So let's start with the expected return of 0 and type in the function that will give us the value of the standard deviation for such level of expected return. So first of all, square root, and then we need to take the square root of a ratio, of a fraction. So in the numerator, we would have alpha and we lock that because we want to enforce the same function for a number of expected returns, times our expected return squared minus 2 times beta, and log the beta again, times the expected return, plus gamma, and gamma should be locked again, and that's the numerator. The denominator is just delta, and that's why we calculated it separately over here, and we lock delta as well, and we close the parentheses and enforce this formula using just enter. And we can see that this formula, this function, heavily resembles something that most of you have encountered in mathematics courses, quadratic equations. So actually, it has a lot to do with that, and if you are interested in the derivation, please consult the original paper by Merton, 1972, that I have put up in the Google Drive of the channel. And actually, that's a good bit to tell you that a lot of additional materials on all the topics I am covering in the videos, all of the videos actually, they are available in the Google Drive that is always linked at the pinned comment under every single video. So check this out if you're interested. But as for now, we're just applying this function derived by Merton using matrix optimization, so we can enforce this formula and also consider a wide range of potential expected returns. So let's take a step of 0.1%, for example, drag this down as well, and drag it all together alongside the expected return and risk, and drag it until we get to 25% expected return per annum. And this actually gives us this very nice curve. And we can see how the efficient portfolio frontier that we have derived using the constants corresponds to individual stocks, represented on this diagram, on the scatter plot, by dots. We can see that Walmart actually lies directly on the efficient portfolio frontier. It corresponds to the fact that Walmart is a pretty good stock in terms of the relationship between its expected return and risk, while all other stocks lie within the efficient portfolio, which means that if diversification is available to an investor could improve both return and risk by considering allocating their capital towards the mixture of these stocks instead of individual stocks. And that, again, is a very persuasive illustration of why diversification is beneficial for an investor and why you should care about modern portfolio theory, at least starting your journey towards learning how to invest and how to wrap your head around academic or industry finance. But that's not the end of the story. The matrix approach developed by Merton also allows you to directly extract a portfolio that is the selection of weights, just as we did with the minimum variance portfolio, given some value of target return. And here we can select particular value of return that we would like to achieve within a year, for example 13%, and then we can actually compute two additional constants and relating them to the H and G vectors, they're again useful here, calculate the optimal portfolio an investor would pick if they had this particular value of target return. Those two constants are lambda and mu, and they are basically just combinations of constants that characterize the investable universe, alpha, beta, gamma, and delta, and the target return. So lambda is a ratio of gamma, so we're referring to gamma all the way up here, minus beta times the target return divided by delta. And mu is alpha times target return minus beta, and all of that divided by delta once again. And we can see that those two constants that we have just derived could be applied as weights to H and G vectors respectively, and used to generate this optimal portfolio that would give us a target return of 13%. So let's do just that. Let's multiply lambda by the H vector over here and add mu times our G vector. And enforcing this weighted sum of vectors by Shift-Control-Enter, we'll get a portfolio with weights summing up to 100%. But if you are uncertain that this is exactly a portfolio that gives you a target return of 13%, let's just multiply these weights by the vector of expected returns over here and see that's indeed the case. We'll get exactly 13% by allocating our capital towards this mixture of stocks. And that's actually why the matrix framework developed by Merton is so useful. First of all, you can derive 4 constants that characterize the investable universe uniquely. They define this pretty curve, the efficient portfolio frontier, and you don't even have to look at all the combinations of the stocks that are possible. You can uniquely define what is the relationship between risk and expected return for the efficient portfolios that some rational investors would prefer. Also, you could calculate the minimum variance portfolio very easily by just looking at H vector and the constant alpha. You can derive the function for the efficient portfolio frontier, and perhaps most importantly, and it's the most useful for practical applications perhaps, you can select a target return and get the optimal portfolio for this level of target return. But what is slightly unfortunate in this matrix optimization framework is that it doesn't allow you to ban short selling explicitly. Because, for example, if you increase your target return and you are less risk averse, you want a high level of expected return, and you want an expected return of 25%, for example, you'll see that the optimal portfolio, the Merton's model suggests, involves shorting, to great extent actually, some of your stocks. And this model is very concise and conceptually simple, but it doesn't have a tidy and neat way of accounting for short selling restrictions. So if you see that your optimal portfolio does include shorts, then unfortunately you'll have to resort to numerical methods, just as we did in the last video with Excel Solver, for example. But overall, this is a very nice introduction to modern portfolio theory, and perhaps it's a good way to stop at that point and reflect on everything we've learned throughout the 3 videos. Diversification is beneficial because sometimes it allows you to obtain the same return with a lower level of risk. It's possible to construct efficient portfolios from even a large number of stocks by applying some matrix algebra or numerical optimization techniques in MS Solver. By no means this is the end of academic developments in the area of portfolio management. There are even more advanced techniques that exists, and for example, you can look at one of the videos I recorded previously on portfolio optimization with higher moments. And there is yet more to learn in terms of portfolio management and investment management. But without this starting building block, this basis of modern portfolio theory by Markowitz and further developments by Merton and others, it's impossible to appreciate all of the further developments that were made through the years. Thank you very much, and stay tuned. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see further suggestions on videos for business, economics, or finance topics you would like me to record. And please don't forget to subscribe to our channel and consider supporting us on Patreon. Thank you very much, and goodbye.